So in this video, we're going to look at some more reactions here for aromatic compounds. We're going to have a kind of a longer list today of new reactions we're learning. But I want to quickly review these electron donating, electron withdrawing groups again. So here we have a compound, right, with oxygen in particular, right, connected to our carbon. So we know this ester group here is electron donating, right, because of this connected piece, and it's in our list, right? So we know we're going to have our bromine adding to one of these positions, right? We have our electrophilic bromine source here. And so the two possible products we can get from these reactions is one with the bromine ortho, and then one with the bromine meta, like we went over during class. It doesn't matter if I draw this ester upside down, right? It's the same no matter what. And on the left side here, or the right side here, we have our cyano group, right? It's this carbon triple bonded to nitrogen, right? So this carbon here is partially positive, right, from the pull of that electronegative nitrogen. And we can get our electrophile here, right, our Br, attached to the meta positions. So in either case, right, no matter where it goes, we'll get the same product, which is the bromine here. And so they have different reactivity, right? So we have to kind of consider that when we're thinking about useful reactions for these substituents. For example, if we're looking at these two different problems here, right, we're starting from benzene, right, in each case, and then we're getting two different products. Right, you see that? In one case, the groups are para, and in one case, they're meta to each other. So if we're doing a retrosynthesis, right, we're starting from one and trying to end with the other, we have to consider how these groups are aligning themselves. And so it's kind of tough to orchestrate that in your head, so we're going to get some practice with this in class too. But we have to consider, especially for this first one, number 3, is we have to add our ethyl group. We want to add the ethyl group first, so it directs para. Okay, and what I mean by that is, right, starting from benzene here, we can have a Friedel-Crafts reaction, right, and we have a short chain, so it's okay that we're using Friedel-Crafts, right? We're not going to be getting any rearrangement happening. And while we may get multiple products, right, remember how we said in class and in the video last time, we can potentially get more than one reaction happening, right? We end with this ethyl benzene, but we can react it further, right, which is problematic. But for these retrosynthesis problems, right, and we've kind of gone over this before, but for retrosynthesis problems, we can just care about one product if we get a mixture. If a mixture is possible. Okay, and I'll reiterate this in class too. So it's okay, we might get multiple products, we're fine ending here, okay? And so from here, right, this ethyl group is ortho-para directing, right? So when we're adding on that SO3H, right, this sulfonation conditions we learned about in the first video, right, it can add ortho or para, but we just care about our para compound, right? We might be getting some of the ortho position, but we only care about our actual product here, right? So this is fine to end here. But, right, that's different than the number 4, right? Because we can't do the same pathway, because there's no way to get that SO3H on the meta position, right? It just isn't possible. The ethyl group is ortho-para directing, so we have to change our approach. So instead of adding the ethyl group first, we have to add the SO3 first. And if we do this, right, it doesn't matter where we get that SO3H added, but for consistency's sake, we'll add it here. And now, right, this SO3H, right, is our meta director. And so we can add here or here. And so when we do our Friedel-Crafts, we end up with, this is our final product. So just by changing the order of how we've added things, we get a totally different final major product, right? Hopefully that makes sense. And like we said before, right, these Friedel-Crafts conditions I keep mentioning are not the best, right? Due to the activation issues it can have. So we're going to look at some other things we can do to add on these alkyl groups, okay? So one thing we can do is actually just reduce down ketones into alkyl groups. So essentially we're just getting rid of the oxygen, right? Turning that sp2 carbon into an sp3 carbon. And we have a few different conditions we can use. So condition A here, we can use this zinc mercury amalgam with acid. This is called a Clemmensen reduction. Second set of conditions we can use is this diamine compound here and base with heat. This is called a Wolff-Kishner reduction, where these are all reduction conditions. And the difference between these two is one is acidic and one is basic, right? These are what we might call complementary conditions. So these are different though, right? We wouldn't use both of them at the same time. We would just use A or B, right? That's important. A or B. But it might change depending on what other things we have on the molecule. Right now it's fine, right? We can use either for this reaction here, but that might change, right, depending on if we have alcohols present. We might not want to use basic conditions because you might get a side reaction occurring with the OH getting deprotonated. And we'll talk about that more when we get to reactions like that. So for C here, our next set of conditions, these might be familiar, right? We can just do a hydrogenation, right? H2, palladium or platinum or any sort of metal with some sort of solvent, something inert like ethanol with these hydrogenation conditions. If I can spell correctly, hydrogenation. These are neutral, but hopefully you remember this. This will also reduce, right, alkenes and alkynes as well. So we have to be careful that we don't have any alkenes or alkynes present that we don't want to reduce as well. So these are all valid conditions we can use for this transformation, okay? But we might want to be careful what other conditions are present, and we'll see examples of this as we go forward. So let's look at some more conditions here. Something else we can do is we can reduce a CH3, or we can oxidize, a CH3 to a carboxylic acid, right? We've kind of seen this with Grignard reagents, right? Attaching on, right, CO2 to carboxylic acid with those Grignard reactions, right? This is also sort of another complementary reaction to that. So for these conditions, pretty simple. These are usually called KMNO4 oxidations, magnesium or potassium manganese oxidations. So these conditions here, right, can reduce a CH3 to a carboxylic acid. Another set of conditions that we can do. Went too far. These will be the last two we're going to look at for today. We have this, again, another reduction happening from NO2, right, just to remind ourselves, to an amine. Right, so this is another reduction happening here. These conditions, again, very similar to our hydrogenation conditions. H2, palladium, and then some sort of solvent, okay? Or we can also use iron and HCl, or we can use tin tin, SN, and HCl. All of these work, but for the most part, we're probably going to stick to these conditions here, right? This is H2O and palladium, right? We've seen this a lot, so this will probably be the first thing that comes to our mind, right? So we can do this reduction not only with carbonyls, but we can also do them with NO2 groups. Okay. So this last one here is more of a doozy. So we can also transform NH2 into a myriad of different functional groups represented by X here. So X can be really anything. So the general format for these is as follows. So we have sodium nitrite, and then H3O plus as a first set of conditions that transforms NH2 into the following compound, N plus, to this compound called a disonium compound, or disonium salt. And so what this is a group that's now a really, really, really good leaving group. And we'll learn more about this actual mechanism taking place in the next video, but it's kind of important to go over now. So this is a really good leaving group because we're making N2. We're just making N2 gas, which is an amazing leaving group, right? It'll leave the reaction as a gas and never come back. So this is a really, really great leaving group. So after we make this disonium salt, then we can add any sort of nucleophile, or a lot of nucleophiles, to change it to something else, right? Nucleophile or X. And I'm going to write off a list of conditions off to the side here that we can use. So instead of nucleophile, we can add, and we don't have to worry about solvent or anything like that, but we can use things like copper chloride, copper cyanide, copper bromine, potassium iodide, sodium borohydride, BF4, H2O. We can use any of these conditions, and I'm going to highlight what gets added here, right? For all these conditions, these groups are what get added as the nucleophile. So for sodium borohydride, we're just adding in the hydride, right, and a hydrogen, fluorine, and then for H2O down here, we add OH, essentially. Okay. And these are all sort of variants of the reaction called the Sandmeyer reaction. And these work really, really well in a lab setting. A lot of these reactions do actually work really, really well. So, right, we kind of have a big list here of new reactions we're learning, right? Especially with number 4 here, where we can essentially add pretty much seemingly whatever we want, thanks to this disonium salt here with N2 plus, being a really great leaving group. And we'll touch more about the actual mechanism of this in the next video. But we're going to look at some examples in class about how we can do these retrosynthesis problems now, right? We're adding more and more reactions to our toolbox, particularly with benzene molecules, right? So we're going to see about adding all these different groups here.